Okay, class, welcome to the last objective in Unit 5, the mole. Objective 3, perform calculations involving mass and moles. Alright, in the last video we figured out how to calculate molar mass, or the mass of one mole. We're going to put that to use right now. Chemists, when they do experiments, like to know exactly how many atoms they're dealing with, because sometimes they want to react them in the right ratios. So, that's what it says here. Chemists want to know how many particles of each reaction, of each type are in a reacting mixture. So, for instance, two particles of magnesium react with one particle of oxygen to produce 2 of magnesium oxide. So there's a 2 to 1 to 2 ratio here, which is important because if we're making this product, we want to make sure that we have our reactants in the right ratio. However, it is impossible to count the particles, so what do? Remember, the molar mass tells us the mass of 1 mole, which is 6 times 10 to the 23 particles. So, we can actually count by weighing, which means that if we weigh out the mass of 1 mole, so for magnesium, that's 24.31 grams, we automatically know we're going to have this many particles. So it may be useful to use this mole map when making conversions, and you'll notice here that at the center of this entire map is the word moles, and that's going to be the most important part of this map, and we're going to kind of use this to organize the calculations we make. In 5.1, we did calculations involving moles and particles. We went up and down right here, either multiplying by 6.022 times 10 to the 23 or dividing by that number, based on what it told us when we made the train tracks. So this was 5.1. In 5.2, you learned about how to find the molar mass. And we're going to come back to this molar volume here in another unit. So for the purposes of this today, you don't need to worry about this section up here. So let's say I was interested in using 3.31 moles of magnesium, and I wanted to know the exact mass of this, so I could basically figure out how many particles there were. Let's take a look at that map again. So we have 3.31 moles of magnesium, and we want to find is the mass of magnesium. So as you can tell by this little map, we're going to need to use the molar mass in order to figure that out. We don't need to know the representative particles here because we're not trying to figure out how many particles are in it. So I'm going to go ahead and set up a conversion, but I'm going to use molar mass as part of my information. So I have 3.31 moles of magnesium, make some train tracks. Now, I know that I'm going to need to put moles of magnesium on the bottom, and I know that I'm going to need to put grams because that's what mass is measured in on top. Now, what do I put here? Well, I already know that the molar mass of magnesium is 24.31 grams per mole, which I got right from the periodic table. So this means it's 24.31 grams per 1 mole. So I'm going to put 1 mole is 24.31 grams. So this says that according to my math now that I need to multiply 3.31 times 24.31, and that will tell me the number of grams I need. The answer to this is about 80.5 grams of magnesium, and that's what my answer is here. So if I want this many moles of magnesium, I just need to weigh out 80.5 grams on a scale. Here's a second calculation, which is similar. This says, how many moles does 25 grams of potassium chloride represent? Let's take a look at that mole map again with our 25 grams of potassium chloride. This time it tells us 25 grams of potassium chloride, and we want to find out how many moles that is. So as you can see, we need to get from the mass to the number of moles, and we need to use the molar mass. None of this is important for us for this calculation. So let's set up ourselves a train track, 25 grams of potassium chloride, and I know I'm going to need to find how many moles, so that's going to go on top, and the grams are going to go on the bottom, and since it's potassium chloride, I'm going to keep writing that. Okay, now I need to find the molar mass, as it said in the previous slide, so let's do that over here on the side. I need to add up potassium's mass and chloride's mass. Potassium has a mass of 39.10 and chlorine is 35.45, and there's one of each. We add them up, we get 74.55 grams per mole. That's grams per 1 mole. So this time, when I go to enter this in, I'm going to make sure that I put that there are 74.55 grams per 1 mole. So the conversion is still using the molar mass in this spot, but I'm just flipping it so that grams cancel with grams. And when I do my calculation, I get 0.34 moles, it's my unit that I have left over, of potassium chloride. And I'm done. Okay, here's a multiple choice question that is similar to the questions that you just saw. How many moles are in 325 grams of ammonium dichromate? Okay, so you have the formula, you know that you're looking for moles, and they give you the number of grams. Go for it. Alright, let's try one last problem. This problem's a little bit different. It says, what's the mass of 5.4 times 10 to the 24 molecules of ammonia? Now this is a new problem because we have grams here. We're looking for grams, but we have particles. We have a molecular amount. So let's go back to our mole map. Alright, so we were given 5.4 times 10 to the 24 molecules of ammonia over here, and we wanted to find the grams of ammonia, which is right here. Notice there's no conversion that allows us to connect mass to representative particles. So what we're going to do is we're going to do this in 2 steps, and we're going to go from the representative particles to moles using Avogadro's number, and then we're going to, once we get to moles, we're going to go to mass using the molar mass. So there are 2 steps, and we have to go through moles in order to get there. Okay, so let's start with a train tracks. We're going to try to find moles first. So 5.4 times 10 to the 24 molecules of ammonia. And so I'm going to put molecules of ammonia on the bottom, which is what I'm trying to convert from, and moles of ammonia, which I'm trying to get. Now we need to put the correct conversion factor in here for moles. Remember, it's 1 mole has this many molecules, Avogadro's number of molecules, not the other way around. So let's do this calculation first. My units for molecules will cancel, leaving me moles, and I get 8.967 moles of ammonia. Now, I'm not done because I need to find the mass of that. And if I'm going to stop my calculation halfway through, notice that I've used a bunch of extra digits, even though I'm only given 2 in the problem. I've used 4 significant digits here. And that's good practice so that you don't create any rounding errors. Okay, let's do the second part of this calculation. I'm going to take my 8.967 moles of ammonia, and I'm going to convert it into grams. So moles of ammonia on the bottom, grams of ammonia on top, and I just need to now use the molar mass for this conversion, as you can see on the chart. So 1 mole of ammonia has a certain amount of grams. I got to again go over to the side and add up my nitrogen and hydrogens, and let me do that first. Alright, so 1 nitrogen and 3 hydrogens comes out to a total of 17.034 grams. So that's going to go up top. And now all I have is some math to do. Notice the moles cancel, so it's now telling me I need to take my mole amount, 8.967, and multiply it by 17, and I'll have my final answer. And our final answer is 152.7 grams of ammonia. And if I wanted to make sure that that was in the correct amount of sig figs, there are 2 here. I'd have to round this to 150 grams of ammonia. And that's it. So that's an example of a 2-step problem where you have to convert to moles right in the middle. Okay, here's a free response question. Determine the number of molecules in 100 grams of hydrogen bromide, HBr. I'll give you a little hint. This is another 2-step problem. You're trying to find the number of molecules, which is down here, and you're given grams, 100 grams, which is right here. So you're going to need more than 1 step. You're going to have to write out your train tracks and set up the factors correctly. Put the math that you did, and then also put your answer in the form below. Okay, see you in class.